Hi, everyone. So today we're going to talk more about the zero potential level. Okay, so in our last video, we talked about how the ZPL, or the zero potential level, for any gravitational potential energy problem is arbitrary. You can put it wherever and the math will work out. So here we're going to prove it. Okay, so we have a 1,000 kilogram roller coaster that is initially at the top of a rise at point A. Right, so we've got rise, point A. It then has a displacement of 135 meters at an angle of 40 degrees below the horizontal to a lower point B. So let's say this does something like that. And we are at point B, right? And our displacement right along there, angle of 40 degrees, and that displacement is 135 meters. Okay, so from A to B, 135 meters. Now, what we want to do first, one, draw, pick, and identify the relevant displacement. So we talked a little bit about gravitational potential energy before and what the displacement is that we care about, right? And that displacement we care about is delta y, right? Because delta UG is mg delta y. So here is one delta y. Here is another delta y. Okay, so we can use this to find that delta y is 135 times sine of 40, okay, using SOHCAHTOA. You can also see that this would also be angle theta, so you could see that this would be 135 sine 40. Or you could use this angle phi and say that phi is 90 degrees minus 40 degrees. And then you could use 135 cosine phi instead of sine theta. Just three different ways to find that relevant displacement. So what we're going to do is we're going to choose B as the 0 point, or the ZPL, and we're going to calculate delta G, or sorry, delta U. So delta UG, okay, potential energy for gravity, is UGF minus UG naught, right, which would be mg times y final minus y naught. Now, if we choose one of these to be our ZPL, in this case, point B is our ZPL, that's our final potential energy, right? So if this is our ZPL, then we can call this 0. Our y final would then be 0, and then we would just find m negative m, I guess here, let's do this properly. You would have 0 minus mg y naught. Okay. Now to find y naught, we would use 135 sine 40. So this would be mass, was it 1,000 kilograms, g 9.81, y naught is 135 sine theta. And this comes out to negative, right? Oh, whoops, I missed my negative. Bad about negatives, because this guy's here, right? Negative 851 kilojoules. Okay, that's if we use B as our ZPL. Now we'll switch to use A as our ZPL. So we will say delta UG equals UGF minus UG naught, right? But now if point A is our ZPL, that means that our potential energy to start out is 0. So then we have mgy final minus 0 is going to equal our potential energy. So we have 1,000 times 9.81. Now we have to find what is our y final relative to point A, right? So if this is our ZPL, right, our yellow dot up there, point A, our our delta y is now negative. Okay, so it is a negative delta y. So we would put negative 135 sine theta, and we will again get negative 851 kilojoules. Okay. Now, just for fun, let's do this. Okay. Just to drive the point home that the ZPL is arbitrary, I am going to put our ZPL right in the middle at 40 meters. Just an arbitrary number. And I'll show you even more arbitrary how that can be. So our ZPL is at 40 meters. So we have delta UG is UGF minus UG naught. The ZPL is between the two, so we can't figure out, we can't cancel any of those out and call them zero, right? So we have mg y final minus mg y naught. Let's simplify this. mg y final minus y naught. Now first, let's look up here. Okay, y final is really easy, right? The difference between here and here, right? That is 40 meters, right? But it is below the ZPL, so that is negative 40. Okay? So here we will have 1,000 times 9.81 times negative 40 minus. Okay? Now let's see our y initial. So our y initial, this is actually a trick that we've already done before. We did this on our last video. If we look at this, we know that this is our initial, right? This is where our initial y naught is. This is our ZPL. If we want the distance between these two, right? We know that this is 135 sine theta. We know that the ZPL is 40, so we would take 135 minus sine 40, right? So let me just show that, right? So if we cut off that 135 sine theta right there, you are left with the difference, and that would be 135 sine minus 40. So let's come back down here and put this in our equation. So then we subtract 135 sine 40 minus 40. Lots of 40s in this problem. So if we put that in our calculator, okay, go ahead and put that in your calculator as well, see what you get. But if you use your parentheses correctly, now there is an incorrect way to put this in your calculator, but you will get negative 851 kilojoules. Okay. Now you can see that our ZPL right here, okay, that negative 40, if you change that negative 40 to any other number between A and B, it may not even have to be between A and B. But if in class, I've changed it to negative 35 and negative 35, you get the same answer. I did negative 70 and I got the same answer. I did negative 1, got the same answer. If you plug this into your calculator and just change those negative 40s, all you're doing is moving the ZPL around and you get the same answer anyway. It doesn't actually matter. The only thing that it's going to change is the math you have to do to get your answer. Okay. So that will lead us into a more important discussion on the next slide. But I wanted to drive this point home that even if you put the ZPL in a spot and you're not sure if it's the right spot, it doesn't matter. You may have done it in a way that makes the problem a little bit more complicated, but you can still get the right answer no matter where you put the ZPL. Okay, now let's talk about our ZPL and conservative forces. So we have this slide here, right? We start at point A, slide down this curvy, slide to point B. Now, in the absence of non-conservative forces, okay, no friction, no air drag, nothing, to find the change in potential energy from point A to point C, do we care about A, the slide being curvy. So no, we don't, right? If we're just worried about gravitational potential energy, we don't care about the path, right? Anyway, so if we go from point A to point B, right? Uh, we don't care that the slide is curvy because the path doesn't matter for conservative forces, right? We talked about that in our last video. Um, right? It doesn't matter for change in potential energy. It doesn't matter if you start at A, go to the space station and back and end at point C. It just cares that you started at A and ended at C, right? So it doesn't matter what happens in the middle. So no, we don't care that the slide is curvy. Now, do we care that the hill size at point B is high or low, right? Do we care about that hill size? So with one caveat, no, right? However, knowing how this energy works, okay, if B goes up higher than A, then you may not have enough energy to make it all the way to point C, right? However, we are operating under the assumption that you can get from A to C within the laws of physics. So if that works, then no, it doesn't matter the hill size at point B, right? It doesn't matter what's going on as you go from A to C at all. That 3.2, it can be 3.3, 3.4. It can be all the way up to 4.99. Doesn't matter. As long as there are no non-conservative forces, right? The key is right here. Absence of non-conservative forces, then it doesn't matter. Okay. Now, part two. Where could I put the ZPL? We could put the ZPL, okay, we could put it at point A. That's fine. We could put it at point C. Whoops. We could put it at point C. That's fine. We just tried that on our last problem. We even could put it at point B on our last problem. We just put it somewhere in the middle. You could even put it at ground level. That works too. Okay. You could find, you could find the height of the Eiffel Tower and say, okay, that, whatever that is, that's our ZPL. Sure, you could. That's legal. Now, the next question addresses the more important topic. Where should you put the ZPL? Now, putting the ZPL at point B, I never recommend. Unless you have a much more convoluted problem than this simple going down a curvy slide, I do not recommend putting your ZPL in the middle. Now, on this problem, I wouldn't even recommend putting it at A. But I tell my students that you can put that point at C or at ground level, and I'll explain why. Okay, C is the lowest point on that slide that you are going to reach within this system, right? The problem is just talking about going from A to C. So if you're only going to C, you can, when you do your delta UG, right, you have UGF minus UG naught. One of those is your ZPL, so you only have to do the math for one of those. That makes things easier. I would say that C is a viable option. However, you could also do it at ground level, and I will explain why. Because yes, you still have to calculate both of those potential energy levels, but when you look at Y final minus Y initial, you don't have to do any math to find out what is Y final and Y initial. Y final is 2 meters. Y initial is 5 meters. This essentially becomes a plug and chug problem. You don't have to do any math to find your height. So I would say that that is also a viable option. Now, whichever way you think is easiest for you to do the problem, that's where you should put it, right? I ask my students where they think they should put it, and it was actually a 50-50 split. Half said C, half said the ground. It just depends on how your brain processes this kind of relativistic idea. Right? But A and B, I don't recommend it. And the Eiffel Tower, that's a stupid idea. Don't do that either. Now, where will the potential energy lost from point A to C go? Right. So we know that as you decrease in height, right, if delta y is negative, then delta UG is negative, right? So if you drop in height, you are losing energy. But where would that energy go? Especially because we are in the absence of non-conservative forces. Well, that energy, okay, UG gets, converted into kinetic energy. You can think of conservation of energy more like an economy than some mystical energy moving back and forth, right? No energy can be created or destroyed, right? That's the rule of conservation of energy. In all of our problems, you can't make new energy or get rid of the energy and destroy it. It's got to go somewhere or come from somewhere. So here, that energy just turns into kinetic energy. It turns into motion. Okay? Now, sometimes energy, even a non-conservative force, right? It's non-conservative makes it sound like it's destroying or creating energy, right? It's not obeying conservation laws. That's not true, because even with non-conservative forces, right, we're going to do conservation of energy problems with friction. So you can actually account for how much energy was lost due to friction. Now, the energy was lost from the system, so that means it's non-conservative, but you can still use that in your conservation of energy problem, right? Even in thermodynamics, you can account for heat loss in a problem as well. We won't do that in this class, but that's also something that you can approach. All right, last, we have the ZPL for spring potential energy. Now, first, starts right off the bat. Can we arbitrarily choose the ZPL for a spring like we do for UG? Quick answer, no. No, you can't. Okay, bad. That is because when you compress or elongate a spring and release it, it's obviously going to move, right? We all understand that that's how a spring works. Compressing or elongating the spring is going to give it the potential to do work, right? Give it to the potential to move an object. That would mean that its only place to set the ZPL is right at equilibrium. Okay? Equilibrium is the only place that you can set the ZPL for spring potential energy. Nowhere else can the ZPL be placed. And this also comes from the idea that work over time is parabolic, right? In the fashion of 1/2 mv squared. Okay, it's nonlinear work forces. So since it's nonlinear, okay, the starting and end values actually matter. Usually, work is linear, right? We've talked about, if we have work as force over time, right? Actually, it's force over distance, I'm sorry. That is usually linear, not a straight line, but you get the point, right? Usually linear. So the starting and end value doesn't really matter. It just matters what is the difference between the starting and ending values. But that's not the case for parabolic, right? That's playing an entirely different ballgame. Now, can the spring potential energy ever be negative? Okay. Also, no. Now, if we look at this graph, okay, spring potential actually has the same equation as work. The work done by a spring is equal to the potential energy that a spring could do, right? If you calculate the potential energy of a spring, you're really just calculating how much work could the spring do if it's compressed to the same distance or elongated to the same distance and you release, right? So same equation. But you notice here that even if you compress it, right, compression is negative, and then stretching is positive. compressing and stretching the spring are negative and positive, but the x is squared. So even if it's negative or positive, you're going to square it and get a positive number anyway. So no, this is not going to be negative. Now I say that again, there is an exception to every rule. The positives and negatives in your problems are usually relative to whatever is positive or negative in your scenario, right? For example, for this problem here, if we wanted to arbitrarily create the positive and negative axis for this, right? Let's say that this is our axis, this is our positive x, and this is our positive y. For some ungodly reason, we want to do that, right? You can do that. You'll still get the same magnitude as everyone else. Your signs might be off, but within your reference frame, you're correct, right? I don't know why you would do that, but you know, some people are just masochists that way. But the potential energy that a spring could do on its own is never negative. It is always positive. You can screw with your relativistic reference frame all you want, but the potential is always going to be positive. Okay. Next, how could the spring K over here, how could the spring K acquire potential energy from block M? Well, the spring's potential energy, okay, is equal to the object's gravitational potential energy, right? So if we have, as that block moves down, right? Let's say that this, right, is our y initial, and let's say that as it compresses, let's say it compresses all the way down to the ground. That means I need to move that, right? We're looking at the bottom of the block. Then here would be the bottom of the block. That would be y final, right? That means that as that block moves, its mgh is converted to 1/2 mv squared. And assuming that there are no non-conservative forces, that would all go to 1/2 kx squared as it compresses the spring, right? So this potential energy is going to go completely into the spring as it compresses the spring at any given distance, right? So this is just an illustration on how energy is converted. It's not created or destroyed, right? All that gravitational potential energy is converted to velocity, but then that velocity is stopped by a spring, and that just means that all of that energy has now been stored as potential energy for the spring. And if we stop it at the moment that the spring stops the block, then we see that it has the potential to spring back. But if we play the whole scenario out, it will spring back, and then they will oscillate. Ideally, if there's no non-conservative forces, they will continue this oscillation forever, right? If there's friction in the spring or friction along the surface, then obviously they will oscillate a little bit until they just settle at the spring's equilibrium. All right, that is what we have for the zero potential level. Next video, we will continue on into the conservation of energy problems and how to work a conservation of energy equation.